Hello friends, in continuation with the last lecture, now we will talk about the remaining dynamic characteristics of an instrument, and we will talk here in this case the second order instrument systems for the second order systems. So let's see the example, that is the U-tube manometer. One of the example is the U-tube manometer. We will show that how this U-tube manometer can give us the second order instrumentation system. Okay, now here you can see is the U-tube manometer. From the one side we can apply the pressure which is kept as open, means through this input signal. Okay, here the pressure is applied at the one end of the tube and the other end is kept open, so that the fluid can easily rise up or the fall of with respect to the changes happening at the other end. This other end is kept open to the environment. Okay, so now the level difference between these two arms of the manometer is h. So the difference between these levels of the liquid in the manometer is considered as or represented as h. Okay, and the pressure P is input one, okay, from the one side, which on the left hand side we have applied, which is considered as the input, and the level difference H is the output. So, what is the input here, or the changing property? That is nothing but the pressure, and what is the outcome of it is nothing but the level difference in the liquid, that is considered as the output one. So we need to here derive the expression or find out the expression between the input and the output relationship. So we need to have the relationship between the pressure and the height within the manometer. So the force on the liquid column is considered as MA. M is considered in terms of its density, that is rho into LA. Okay, LA is its volume and the V is the density of that liquid, d2h by dt square. So this is acceleration of the liquid within the tube. So d2h by dt square must be equal to the, now this is equated with the force due to the gravity. How much force is because of the gravity is acting on it, that is h rho ga. The pressure force is Pa, and the frictional force between the tube and the liquid wall, that is delta Pa into A. So these are the forces which are acting on this liquid which is moving into the liquid column. Now force of the liquid column is given as rho La d2h by dt square, where the rho is the density of the liquid column, L is the length of the liquid in the column, and A is the area of cross section of the tube. Pressure force is given as a pressure into the cross sectional area. Gravitational force or the gravity force is h rho ga. Here the friction force, that is delta P into A, where delta P is the pressure loss in the tube, and which is given by the Poiseuille's equation, and is a standard formula, that is delta P is equal to 128 mu L Q by pi d raised to 4. Here d is the this d is the diameter of the tube, where mu is the viscosity of the liquid, and Q is the volume rate of the flow of the liquid. So this is the rate of flow of the liquid within the tube is represented with Q. Now here we have the Q. We know that the rate of flow of liquid within the tube is given by Q V into A. So it is represented with the Q. So Q is equal to V into A. V is the velocity with which the liquid is flowing, and the A is the cross sectional area. Where we can have the V is the velocity, that is dH by dt, because height is only changing parameter with respect to the time, and A or cross sectional area is given by pi d raised to d square by 4. Instead of having the pi r square, we can have here the pi d square, its area. Substituting the value of the Q and the delta P from these above equations, we can get the Q is equal to pi d square by 4 into dH by dt. We just substitute this value in this equation. So the friction force is 8 pi mu L dH by dt. So we have calculated the friction force here. Now we'll just try to collect all these above equations, and we get the rho LA d2h by dt square, which is equal to the, this is nothing but the our pressure force into h rho Ga. This is liquid force on the liquid column, and this minus 8 pi mu L dH by dt. This is because of the flow rate force which it is there. So just rearrange the terms and rewrite the equation on the left hand side as the function of h, and on the right hand side is the constant, is force p, pressure p. So rho L d2h by dt square plus 32 pi mu L by d square into dH by dt, h rho g into h, and h can be taken out, and this is equal to the some constant p. From this expression we can consider that the U2 manometer is an example of the second order instrument, because there is, this is the h is the output and the p is the input, is the applied pressure. So we have found out the relationship between the output and the input, and this is second order differential equation. That's why we consider that this is the second instrument. The another example will talk about this, the seismic motion transducers. Seismic one, the vibrations happening inside the generally earth crust, or within the earth, the what are the vibrations are there, that has to be detected. Generally we use the seismology, right? But it is not only related to the detecting the vibrations within the earth, we can use it for the some instruments as well. So it is basically a displacement transducer which is used to measure the vibrations produced in the base of the instruments. At the base, in the base, how much are the vibrations are produced, and that has to be detected, and how it can be avoided, okay, while doing some kind of the measurements. Here the P and R are the displacement of the base and the mass relative to the frame, which are input and output of the system respectively over here. So this is the schematic representation of the seismic motion transducer. A transducer, it converts the one form of energy into the another one. Here the construction of this device or transducer is something like, on the here we can see the scale bar over which the pointer is moving. This is the recorder, pointer is moving on this record. So this part is the recorder. Mass is attached or hanging to the frame through the spring, as well as the some tube or the container having the liquid, and the damper is. So this is a damping mechanism through which we can detect the vibrations within the this material one, okay, as the mass object which is placed. And on the one side there will be the displacement q, which is represented, and that depends upon the pressure. So pressure is detected from this side, so pressure is represented or changed by this scale. In this direction we can apply pressure. The equation of the motion obtained from the internal forces of the mass, restoring force of the spring and the damper, which is given as m d2q by dt square plus d into d by dt q minus p into plus s into q minus p is equal to 0. Here m is the mass of the body, s is the spring constant, d is the damping constant of the damper. So here d is the damper over here, and this d is the d by dt, yeah? So don't get confused here. So the relative motion of the mass, which is given by z is equal to q minus p. Okay, this is some another variable we use here instead of the q minus p. And m d2q by dt square plus d into d q minus p, d by dt of q minus p plus s into q minus p is equal to 0. So on substitution we get the equation like m d capital D square plus small d into capital D plus s into z1, q minus p is z, is equal to minus d square p. So this remains a constant one. So we can have the relationship between the z and p. This is out parameter and this is the input one. So from this equation we can consider the seismic motion transducer is example of the second order instrument. Thank you.